Let's now move on to the filtering or state estimation problem. And let's start with a single object that we want to track before moving to multi-object tracking in Unit 3. Before we start, let's first understand better the difference between state and observation. The hidden state are the parameters of interest, for example, the object location or velocity in 2D or in 3D, or maybe the joint angles of that human body, etc. The observation, in contrast, is what we are able to directly observe. This is the measurement. Now, the hidden state and the observation are not necessarily the same. First, the observation is typically a noisy version of the true state because our sensors suffer from noise. We can't exactly estimate the position. The object detector result is noisy, and we have to accept that. And furthermore, not all aspects of the state might be directly observable. The state may only be partially observed. For example, we may be interested in tracking the velocity of that ball, but we are only able to observe the position of that ball. And that's why the hidden state that we want to track over time may not be the same. In most cases, is not the same as the observation. And that's the reason, of course, why we need filtering and state estimation. For now, let's assume that we have only a single object which we want to track. This is something we'll assume throughout this entire Unit 2. The moving object of interest is characterized by an underlying state x. So x, bold X, we denote here a vector. This is a state vector. State x gives rise to measurements or observations, which we call y. So for every state, corresponding to every state, we have a measurement vector y. At each time t, the state changes to xt. Changes from xt minus 1 to xt. And we receive a new observation at that time, which is called yt. In other words, we are simply indexing the time dimension using the time index t. Now, given a sequence of observations y, which is summarized with this capital Y letter here, we aim to recover the state, which we summarize with the X letter. So this is the observations across all time instances, across all frames, and this is the states summarized into a set across all frames. And here at the bottom you can see the graphical model for this process, which we'll talk about more in a few slides. But you can already see that this is corresponding to what we want to solve. We have a hidden sequence of states here with the non-filled circles. These are the variables that we want to estimate and that are unknown to us. And for example, the state at time t depends through some motion model on the state of at time t minus 1. And the measurement that we observe, this is why this node here is highlighted in gray, this is an observation, depends on the state at the corresponding time instance. So we have a measurement at time t that depends on the state at time t, and we had a measurement at time t minus 1 that depends on the state at time t minus 1. And then the state at time t depends on the state at time t minus 1. And of course, that continues backwards and forwards in time. But for simplicity, I've just drawn these two time instances here. Okay? Now, this is how this is reflected in the simple 1D example that we have already seen. In this case, the measurement would correspond to the dashed line. This is what we call y. And the estimated state would be the green line. Now in tracking, we're dealing with uncertainties in the state and in the detections, and so therefore we often aim for a probabilistic estimate, not a point estimate. We want to track distributions over time. For example, distributions about the object location over time. And that's why we'll have a short probability theory recap now to refresh ourselves on probability, very briefly only, and to prepare us for the so-called Bayes filter, which is the general framework that we consider here in this unit, and that heavily relies on the so-called Bayes formula. So here's the recap. In probability theory, we're considering random variables. For example, discrete random variables that take values from a label set. And in this case, the probability that x takes a value c is denoted as p of x equal to c. And then we have continuous random variables. And in tracking, we most frequently consider continuous state spaces. It's not always true. There's also discrete versions of these filters, but in this unit, we are considering mostly continuous variables, so that's what's relevant here. And the probability that x takes a value in A is denoted as such in a subset of the domain. Now, the distribution over a random variable we write as p of x, and the joint distribution over two random variables we denote as p of x, y, which is basically a shorthand notation of p of x equals c, etc. Okay? There's two fundamental properties, two fundamental axioms in probability theory. The first is called the sum rule or marginal rule, and the second is called the product rule. The marginal or sum rule tells us that p of x is equal to the joint distribution if we sum over all the state of y. Or equivalently, for the continuous case, p of x equals the integral over y of p of x and y, the joint distribution. And the product rule is simply telling us that p of x and y, the joint distribution, equals the conditional distribution p of x given y times p of y. So I assume that you have heard about these before. Based on the product rule, p of xy equals p of x given y times p of y, we have the following relationships. So first of all, we have p of xy equals to p of x given y, p of y. And then, of course, we can also reverse the order of these two random variables inside that probability distribution, which doesn't change anything. But this means that we can write this conditional or this product here also in terms of p of y given x, the conditional distribution of y given x. Note that here we have x given y, here we have y given x, times p of x. And if we now solve this expression in the middle here, this equation, for p of x given y, or in other words, if we take p of y and put it in the denominator here on the other side, then we obtain the famous Bayes rule. P of x given y, the posterior, equals p of y given x, the likelihood, times p of x, the prior, over p of y. Similarly, we can consider the joint distribution over three random variables, p of x, y, c. And we can again swap x and y here, and we obtain this equation. And we can solve this equation for p of x, y, c, which is this expression here, by putting this in the denominator, and we get this expression. Now, if we look at this expression, we see that, well, here we can replace these two through the product rule with p of x given c and p of c, and here in this case p of y given c times p of c. We have simply applied the product rule here to these two terms. And then we see that p of c cancels. And so we obtain p of y conditioned on x and c times p of x conditioned on c over p of y conditioned on c. Why did we do this? We do this because we now see that the Bayes rule also applies when conditioning on another random variable c. And this is colored here or highlighted here in red. So the only thing that has changed to this formula here is now that we have added an additional condition that's the same in all of the terms on the left and the right hand side of this expression. So we condition on any variable and base rule still applies. Now, we of course did this for a reason. We did this because this is a rule that we're going to need in order to derive the base filter. So keep that in mind. Let's move on to the base filter now. It's also called recursive Bayesian estimation. In recursive Bayesian estimation, we assume that we have only a single object which we want to track. Further, assume that exactly one noisy observation is available per frame. So we don't have an association problem. We want to do probabilistic state inference. That is, we want to estimate distributions. And the recursion Bayesian estimation or base filter approach is a probabilistic approach for estimating an unknown probability density function recursively over time using incoming measurements, for example, the detected object locations that come from the object detector, and a system process model, for example, a constant velocity motion model. And it involves two alternating steps. The first step is the prediction step, where we predict where the object should be in the next frame based on the previous state. For example, if the previous state includes the position and the velocity, based on this we can predict the position in the next state. And it involves a second correction step where we correct the prediction based on the current observation. The prediction doesn't yet know anything about the current observation, so we are integrating that current observation back into the prediction. You can think of this as building a weighted sum between the prediction from the motion model and the actual observation. As a little remark, a good motion model is not only necessary here for making a good prediction that we can then easily correct, but it's also important for association, obviously, because if we have a lot of detections and our predictions are very accurate, then it's very easy to find the correct detection that corresponds to each prediction in the next frame. So while we are deriving the Kalman filter here, or the base filter here first, the Kalman filter is a special case. But as we are deriving the base filter here for a single object, of course, once we solve the association problem, we can apply this base filter for all objects that we have associated, right? So it doesn't mean that this filter only works for a single object, but without association and considering only a single object, the problem becomes easier to look at. Before defining the base filter formally, let's first look at the assumption that we're making here. It's always important to think about the assumptions that we're making for certain models that we're looking at. So general assumptions that we're making are that the camera is not moving instantly to a new viewpoint. It doesn't jump. We're having some smoothness. And that the objects don't disappear and reappear in different places in the scene. And that there's a gradual change in the pose between the camera and the scene. What this means is effectively that things happen smoothly. Things move smoothly. And that's why we can exploit the models, the motion models, for example. There's also certain assumptions on the motion and the observation model that we employ. For example, the base filter assumes that the state follows a Markov process. We are actually modeling a hidden Markov process, a hidden Markov model. A Kalman filter, which is one of the simplest continuous base filters and has a closed form solution, assumes further a linear and Gaussian motion and observation model that seems pretty restrictive, and indeed for many applications it's too restrictive, and therefore more advanced models have been developed, such as the extended Kalman filter or the unscented Kalman filter or the particle filter, which are less restrictive. Now let's start by defining the base filter formally. let xt denote the true hidden state of the system at time t. xt is a vector of real numbers of dimension m. Let further yt denote some noisy measurement of xt at time t. The base filter assumes that the state sequence is an unobserved Markov process and that the observations are the corresponding measurements. Here you can see the so-called graphical model again from the previous slides, where the state depends on the previous state, the state at the previous time, and the observations depend on the state at the corresponding time. But the state does not depend on the state, does not directly depend on the state at earlier time steps, and the observation does not depend on the state or observations at earlier time steps. This is the so-called Markov property, and that's why it's called a hidden Markov model. We have a hidden layer here, which is the unknown states that we want to estimate, and we are obeying the Markov property that I just mentioned. This means that the probabilistic formulation of this model is very simple. The joint distribution of all observations, all states, and all observations across the entire sequence can be simply factorized into the prior distribution over the state at the beginning of the sequence times the product over the motion model that transitions from time t-1 to time t. The product goes over all time steps, as well as the product over the observation model at each of these time steps. Right, so this is a directed graphical model, a Bayesian network, and this is the corresponding factorization of that Bayesian network. The goal now is to perform inference. In other words, to estimate x from y in this hidden Markov model. How do we do that? For this recursive state estimation problem, we take advantage of Bayes' rule. More precisely, we take advantage of exactly the rule, this conditional rule that we just derived. Let's consider the posterior. The posterior is the probability of xt, all of the states from time, the posterior is the probability of state xt given all of the observations from time 1 to time t. This is what we want to estimate, right? This is the solution to the inference problem, if you will, this distribution, because this tells us what is the probability of the state at time t given all the previous observations and the observation at the current time. Now we can reformulate this using this conditional form of the Bayes rule as such here, where we condition on y1 to t-1. So this notation here means I'm taking all the y's. This is the set of all the observations from 1 to t-1. It's kind of MATLAB notation. And so this is the conditioning variable which was read in the simple example before. And then we have the Bayes rule applied here, which is yt given xt times p of xt over p of yt, right? So this is just the formula from before. Now what we observe here is that in the denominator we have a constant because x doesn't appear. We don't have any random variable. These are just observations. So we can absorb this constant into the proportionality symbol here, which means that the posterior is proportional to the observation distribution times the prediction. This is the first term here, and this is the second term. And what you see is that this term is slightly different from this term here. And why is that so? Well, that is because we have made use of the Markov properties that we have assumed. We know that the variable yt conditioned on xt In other words, this variable conditioned on this is independent of all the other previous variables, which means that this distribution is equal to the probability of yt given xt, and that's simply the observation model. And then here we have the prediction on the right hand side, which is estimating the distribution of xt given all the previous measurements. This predictive distribution on the right can be further decomposed as follows. I colored it red here to illustrate it better. So this is the one that we want to decompose. We're going to decompose it as follows. We're first going to consider this predictive distribution as the marginal distribution. See, we're marginalizing here because we have an integral over a random variable, the random variable xt minus 1, that we have inserted on the left-hand side before the conditioning symbol here. From the sum rule, these two expressions here are similar, or are the same. Right? So we haven't changed anything, we have just marginalized xt minus 1 to yield the predictive distribution. Now we can apply the product rule again. So we apply the product rule to factorize this distribution into p of xt given xt minus 1 and y1 to t minus 1 times p of xt minus 1 given y1 to t minus 1. And now again, we can make use of the Markov property. We know that xt given xt minus 1 and y1 t minus 1 is equal to xt given xt minus 1, because if I know xt minus 1, if I want to estimate this predictive distribution here, and if I know xt minus 1, then I don't need to know the previous variables here in this directed graph. So this is again the Markov property that we have exploited. So this expression here simplifies to this one here, which, as we see now, is simply the motion model. It tells us how the current state is distributed given the previous state. That's what we call the motion model. And what we also see is that on the right-hand side here appeared the previous posterior distribution. This is exactly the same expression as we have started with here, except that the index t has been replaced with the index t minus 1. So it's the posterior for the previous time step. And so now you can see how we end up with this two-step procedure where we alternate between prediction and correction. We obtain a recursive state estimation algorithm. The prediction step is this second formula that we have just derived, where we derived the predictive distribution, and the correction step is then the first equation here, where we get the posterior at time t from the observation and the prediction. And so we are alternating these two at every frame. With every new observation, we are first making a prediction about the state, and then we're integrating that observation in order to get the posterior. And then we start again in the next frame. So the filter runs online. We do one update per frame. Now there are some special cases to this base filter, and the most prominent by far is the famous Kalman filter. If the motion model and the observation model are both linear and normally distributed, we obtain the Kalman filter. And so in this case, we're tracking a Gaussian distribution. So we're tracking the parameters, which are the mean vector and the covariance matrix. The solution for the Kalman filter is given in closed form as the products and marginals are Gaussian. Right? So we have assumed that the motion model and the observation model are Gaussian. And because in these equations here, we only marginalize and we only compute products, we obtain a Gaussian as a result. And it also means that the maximum likelihood solution simply corresponds to a least squares fit. So I'm omitting the formulas here because they are slightly technical, but we obtain a closed form solution. That's the key message here. So it's very simple formulas, but of course it makes strong assumptions. It assumes the motion model and the observation model are linear and Gaussian. The Kalman filter is the optimal filter in least squares sense. But there is nonlinear extensions as mentioned before. For example, the extended Kalman filter, EKF, or the unscented Kalman filter, UKF. And multiple modes, which cannot be handled by the Kalman filter because we are tracking a unimodal Gaussian, can be handled by extensions such as the particle filter, which computes a sampling-based approximation to the state posterior. So if you expect to have a highly multimodal distribution that you want to track, then of course a Kalman filter doesn't do the trick. You need something more advanced like the particle filter. And more recently, learning-based motion models, for example RNNs, have also been explored. So you can learn them jointly. Now coming back to the Kalman filter, tracking a Gaussian distribution, the state represented through a Gaussian distribution. Here's a simple example. We start with this distribution here. This is the distribution of, let's say, the location x of that object. The first thing we do is we apply a deterministic drift, which is basically corresponding to the prediction. And we have a stochastic diffusion because through this prediction we become more uncertain about the state. So you see that the variance has increased. But then we also integrate the new measurements. As you can see that now the variance decreases again and the distribution gets closer to the observation. So we're averaging the effect of the prediction and the observation, if you will. Examples for motion models are examples for motion and observation models are, for example, in the constant velocity case, a simple setting where the state vector is the position and the velocity. So we have xt equals position at time t and velocity at time t. And then we can write the motion equation as xt equals this matrix times xt minus 1, which effectively means xt equals pt minus 1 plus delta t times the velocity at times t minus 1 plus, so this is the deterministic part, plus the stochastic part. We have this epsilon here, which is sampled from a Gaussian distribution with zero mean in this case, and a covariance matrix sigma m for motion. And similarly, we have an observation model, which is given here on the right, where in this case we simply pick out the location from that state vector, and this is our yt, corrupted again with some Gaussian noise. Well, actually that should be non-bold. This should be one-dimensional in this case because we have a one-dimensional variable. I will fix that. And similarly, we can define a 1D example with constant acceleration, where now the state vector includes position, velocity, and acceleration. And it's, the state transition happens with this 3x3 state transition matrix. And again, we have Gaussian noise for both the state transition, for the motion, and also for the observation here. So these are two cases that can be solved optimally through the Kalman filter because we have a linear model for the motion model and for the observation model, and both of them are Gaussian. However, there's many cases where this doesn't work in the real world, that are nonlinear and that require nonlinear models. For example, here you can see an example where we have nonlinear dynamics. The pedestrian is not walking linearly, it's bouncing up and down, and also this bouncing ball here. If you would use, for example, a constant acceleration model, then at this point we would predict in the next frame the prediction to be of this ball to be here, but actually it bounces back. And so the prediction would be too far from the true position to yield a meaningful correction in the correction step. And it would strongly violate the linear model. Now, let's look at some results. Here we can see the result of tracking a dog. And what you can see is in the background, the white square corresponds to the detection. You can see that it's jumping around as it's noisy. And the smoothed version is the red box. That's the output of this Kalman filter here. So this illustrates again that the filter is filtering out the noise. That's where the name comes from. And so here's another example where the tracker is following the observation here. The observation is in red and the tracking result, the estimate, is in white, and you can see how it is able to smooth out some of the noise, but there's also some lag or some delay introduced in the tracking. The Kalman filter has been used in many applications, and one of the most famous ones is the moon landing. And there is an interesting quote which I wanted to show you in this publication here, Engineers Look to Kalman Filtering for Guidance. The Kalman filter was used, for example, in the Ranger, Mariner and Apollo missions of the 1960s. In particular, the onboard computer that guided the descent of the Apollo 11 lunar module to the moon had a Kalman filter. According to William Lear, an aerospace engineer, NASA contacted him about 9 months before Apollo 11's scheduled launch because their Earth-based tracking program wasn't working. Lear wrote a 21-state Kalman filter program which went into the Doppler radar system. The final check of the program, Lear recalls, was done the day before Armstrong, Aldrin and Collins took off. So it's not just us that work close to the deadlines, I guess. I hope that Armstrong, Aldrin and Collins didn't know about this. Okay, so let's finish this unit with some pointers to further readings. If you're more interested into the technical details of the Kalman filter, of course, Wikipedia is a great resource. But there's also this book from Forsyth and Pons called Computer Vision, A Modern Approach. And it has a good introduction to tracking and to Kalman filters in chapter 17.